digital video processing, it also requires that the stream has to be in a digital format. And so again, we perform sampling and quantization for the digital video as well, like how we do for images. So now here video quantization is very much similar, but sampling is a little more complex because it has time dimension. Quantization is basically giving colors to each and every pixel, giving intensity values to each and every pixel. So that is similar, but sampling is little more complex. Now here, spatial dimension, unlike any other spatial dimension like x and y, time always moves forward. That is, x and y values can move in any direction. It can reduce or it can increase, but time always moves in that is positive direction only. So now real time processing needs that the result has to appear instantaneously, and the processing, it cannot depend heavily on the future video samples. That is, whatever processing has to be done so that the video is getting displayed, it has to be irrespective of what's going to happen in the future. With the current data only I should do it. So now, because of the large volume of video data, videos are generally larger in size, and so we need good hard efficient algorithms and also hardware for this. So here, there are analog video systems like televisions and monitors which are used to play this particular video. Now, what happens here is there is a one dimensional signal which is obtained at x, y, and t. That is, along the space direction and in a particular time. That is, it's basically rendering every pixel by pixel. Now this is called as scanning. That is, I am determining at y and at y space, at t value, what will be the intensity level. Then at the next x1, x2, at y and t, what will be the value. So basically it's giving me value by value, and that process is called scanning. That is, it is converting that one dimensional, it is making it as a one dimensional signal by, and it, what is the frame receiving? The frame is receiving x, y, and t, and that is being converted to a one dimensional signal. That is basically scanning. And what we get after scanning is pictures or the scan lines. So now here the result is nothing but a series of complete pictures called as frames, and each frame has multiple scan lines. So scanning is the process of converting the two-dimensional image into a sequence of electrical signals by examining the image line by line. Now, with the help of this particular signal, that is, I'm converting the 2D image to a 1D electrical signal, and here why am I doing this 2D image into 1D time varying signal? So that the image can be transmitted, stored, and displayed. So now there are two types of scanning. One is the interlaced scanning, another one is the progressive scanning. Now progressive scanning scans each and every line by line, top to bottom. This is how this is what is being done in computer monitors and modern displays. So if the refresh rate is 1 by 72 seconds per frame, that means 72 complete frames are displayed every second. It has good image quality and better motion representation. The next one is now refresh rate, as in the number of times information is displayed per second. So now if I say 72 frames per second, that is my refresh rate. If it's a low refresh rate, then it causes visible flicker. Otherwise, if it is usually 50 frames per second is perceived by the human eye. Less than 50 frames per second is perceived as flicker to the human eye. If it is more than that, then it is fine. So television systems have limited bandwidth, and if I do progressive scanning here, then it is going to take more bandwidth and reduce spatial resolution, and so one solution to that is interlaced scanning. Now in interlaced scanning, it will not refresh the entire frame at once, rather it will refresh odd lines and then the even lines. If it is 2 is to 1 interlacing, then it is odd lines and the even lines. If it is p is to 1 interlacing, then it is every pth line. Let's say every third line or so. So now these partial images are called fields. And then after that, once I scan, let's say all the odd lines, then I scan all the even lines, put together it will form one frame. So I might first do for this, then I might do for the odd lines, and then after that, put together what I will get is one frame. Because these are having lower bandwidth, they do not have such good hardware so that they can process all at once. So this 2 is to 1 interlacing, where it is odd lines and even lines, this is used in traditional TV systems. But the problem of drawback of interlacing is that it can cause blurring, jagged edges, motion artifacts. All these are possible. That is, some blurring, jagged edges might be visible. So how do they TVs reduce interlacing problems? They reduce interlacing problems by using known as phosphors. Now these phosphors, they have a light emitting nature. That is, they can continue glowing for a short period after being excited, and that property is called as persistence. So that means the light behind each and every TV pixel remains on till the next frame is getting refreshed. So one field remains visible until the next matching field arrives. So that helps to reduce flicker and motion artifacts. So here, as you can see, here it is progressive scanning on line by line, and here you can see these darker lines refer to odd lines, and then it is the even lines, this line, and so on.